Okay, here we go. All right, so moving on down to percent composition. Remember, percent composition is really pretty simple, right? You're going to have, it's just like calculating your grade, right? Whatever, well, especially in this class, right? We have different categories. We have a test category, we have a quiz category, lab category, a homework category, and they each have different percentages that make up your total grade, okay? And what we want to do is essentially, that's what we're kind of figuring out here. We're going to take the mass of that element in that compound and divide it by the total mass, molar mass of the entire compound. And that's how you can figure out what the percent composition of each element is. So, for example, we'll work the percent composition for each element in, what's the name of that compound? Sodium carbonate. Okay, sodium carbonate there. All right, so we need to have a periodic table and a calculator out, right? I'm going to start my calculator. There we go. I don't know that I can expand. Oh, I can, maybe. There we go. Okay, great. I don't have my clipboard, my calculator, but I have this right here, so I can open up my periodic tables. All right. So here we go. So first thing we want to do is we got to find the molar mass of that compound. All right. So, oh, hello. All right. So first thing we want to do, find the molar mass of this compound here, right? So we got 2 times 22.99, sorry, plus 1 times 12.01 for carbon, and 3 times 16. And that will give us our total molar mass for this compound, right? So 2 times 22.99 plus 12.01 plus 3 times 16. I got 105.99 is our molar mass for that compound. All right, double check my math and stuff, make sure we're doing okay. All right, and if we want to find the percent sodium that's in that compound, what we do is we take the total mass of sodium that's in there, right, and divide it by the total mass of the entire compound. Okay, so pretty simple, right? So for percent sodium, that's going to be equal to 2 times 22.99, right, divided by 105.99 times 100. Hot in here. Keep these doors closed, keep the AC in here. It's all like warm. Fans are off. Okay, so then when we do that, we're going 45.98, right, divided by 105.99. So that's going to be equal to 43.4%. You go 3 sig fig, is that what you got? Okay, all right, so I'm going to keep going. So the percent carbon is 12.01 divided by 105.99 times 100. We get 11.3%. And then the last one there is percent oxygen. So we got 3 times 16 divided by 105.99 times 100. You guys might notice a lot of my calculator, I tend to hit enter after a lot of things that I do. Okay, and the reason why I do that is because I tend not to like to put everything all at once in and use all the parentheses and everything else, because your calculator is going to it'll do exactly what you tell it to do. So if you screw up the order of operations as you enter in like as you input the calculation, it's going to spit out a number for you, but it might not necessarily be correct. Okay, and that's especially important when we start dealing with like Avogadro's number, and we start to get big like scientific notation going on, and sometimes your calculator is kind of dumb, and it will take that little times 10 to the 23rd part, and it might actually multiply the 23 times something, and then it starts screwing things up. So just be aware of that, okay? So then ultimately we get 45.3%. Okay. And that actually works out pretty good to give us 100%. So that's pretty nice. It should be pretty close. It won't always be identical when we round to 3 sig figs to 100%. All right? Just FYI with that. Okay? So that's percent composition, right? So you find the part divided by the whole times 100. There you go. Okay? And you're just doing that totally based on mass. Totally based on mass. All right. Now with empirical and molecular formulas, right? The empirical formula is the most simple formula for that particular compound, okay? So what I mean by that is a molecular formula is the exact formula for that substance, okay? But the ratio between the elements in there, okay, might be smaller, and that's the empirical formula. The empirical formula is basically the smallest whole number ratio of the elements in a compound. Okay. Smallest whole number ratio of elements in a compound. All right, and in some cases, the empirical formula will equal the molecular formula. For example, like water, right? H2O. You can't combine those in any smaller ratio than 2 hydrogens, 1 oxygen, okay? But there are other substances out there where you could have 4 hydrogens and 2 oxygens, okay? And that would be the molecular formula for that particular substance. All right, so for example here, if we look at down here on the bottom, we have octane there, okay? That's octane. All right, C8H18. 8 and 18, right? These are all, this is molecular formula here because we can reduce the 8 and 18, right? They're both divisible by 2, right? So we can divide that down and get it down to, right, C4H9, right? That would be the empirical formula, okay? So here's the empirical, this is the molecular. All right. Now, hydrogen peroxide here, H2O2. We can get that down to a lower whole number ratio as well, right? Just to be HO. Okay. So that's the empirical. This is the molecular, right? H2O, right? H2O. Can we reduce that down anymore? No. Okay. So its empirical formula is H2O. That's it. They're the same. Yes. No, because we're not worried about hydroxide has a charge, right? Yeah, so it's different. Okay, so here we're just looking at the ratios between the two, between the elements that are in the compound, and no charges are really taken into account. Okay. All right, so we can use percent composition to figure out the empirical formula for a compound. All right. Now, and this is where this is it right here, man. It all boils down to this. Okay. 1, 2, 3, 4 steps. Okay, these 4 steps. Now, okay, this part's put out like here are the nitty-gritty directions. Okay. All right, the jingle does those for you, right? Okay. Percent to mass, mass to mole, divide by small, multiply till whole. Yeah, right? Boom. Fifth. Percent to mass to mole, divide by small, multiply to a whole. Right? Boom, and then you gotta like, a little human in here, my shoes are sticking to the tile. Right? So I can't spin like I normally spin. Okay? Oh, you can just hear me rap it over and over again. Hey, hang on. Okay, so percent to mass to mole, divide by small, multiply to a whole. Like that, all right? So when we're doing percent composition, right, you've got 100% of something, okay? We're just going to assume when we say percent to mass, we're talking about, all right, we'll just change the percent into mass. So if we assume we've got 100%, assume we got 100 grams, okay? We got 100%, we're going to break that up into grams. So, for example, 5.9%, hey, we're just going to change that percent into mass, 5.9, all right? 94%, 94.1% oxygen, we're going to turn that into 94.1 grams. Real easy, right? Because if you have 100 or something, it's simple, right? It's very simple, all right? And the next part, the mass to mole. So the mass to mole part is where we take the grams and convert into moles. Okay, so here in this case, we took hydrogen, converted into moles. All right, oxygen, converted into moles. All right, notice though, this is one key thing though, right? We aren't worried about diatomics when it comes to empirical formulas. Okay, because we're just looking for the simplest ratio between the singular elements in the compound to each other. Okay, so when you do the conversions, don't worry about diatomic elements here. All right, and then what we want to do is we want to divide by small, and then we'll multiply to whole. Okay, so let's try one out here. Okay, so we've got our empirical formula there. It's got a compound composed of 43% sodium, 11.3% carbon, and 45.3% oxygen. Right, so that's we just want to work it on here a little bit. Okay, so percent to mass. So what I'm going to do, 43.3 grams of sodium. Okay, I got 11.3 grams of carbon. I got 45.3 grams of oxygen. All right, and I want to do mass to mole. So I'm going to convert all of these guys into moles. Okay. So in 1 mole of sodium, there are 22.99 grams. 1 mole of carbon, there are 12.01 grams. 1 mole of oxygen, just O, what we're looking at, we have 16 grams. Okay. So then we got to convert these into 43.3 divided by 22.99. So 1.88, 11.3 divided by 12.01. We got 0.94, 45.3 divided by, come on, 16. We got 2.83. All right. So now, we did percent to mass, mass to mole. Now we're doing the divide by small. Divide by small. So what that means is we want to take the smallest number we have here and divide them through all by that number. Okay? So we divide by 0.94 here, divide by 0.94 there, and you divide by 0.94 there, right? So we're getting the ratio of these guys to one another. We got 2.83 divided by 0.94. Whoop. So we ended up getting 3.01. Is 3.01 pretty close to 3? Yeah. Okay, so it's just 3. There you go. Okay. Oh, we have whole numbers here at the end. So the last step there, multiply to the whole, we don't have to do because we have whole numbers. We have whole numbers here. Okay, so then our formula is just Na2C1O3. Boom. Okay, so we did the first three steps. The last step we didn't have to do. And we're going to do another example here where I think we have to. Okay. So let's see. I'm going to jump down to the molecular formula one because we'll go through all the steps here. Okay. And actually, right before I do that, let's do this real quick. We'll shoot down here, go sample problem. Okay, for this one here, so we worked through an empirical molecular formula problem. Now, the one difference with these is they're going to be like, all right, well, here's a percent composition for this compound. They give it to us, and they're like, all right, well, the molecular formula has a mass of whatever. Okay, so remember that the empirical formula is just the lowest whole number ratio of those elements to the molecular formula, right? So, for example, right, we might have something like, let's say we got H2O, right? Or actually, it'd be easier just to do. Right, let's say we have CH4, okay, and then maybe we have C2H8, okay. How many of these go into here? It's easy to see that, right? It's easy to see that, okay. But let's just say we know the mass of this guy is, what's that, 12 plus 4? It's basically 16, right, grams per mole here. All right. Let's say that our molecular formula mass has a mass of 48 grams per mole. What's the molecular formula of this one? Yeah. C3H12. How did you get that? Right. 48 divided by 16 gives you 3. So you can see the empirical formula goes in there 3 times, right, based on the mass. Right? And that's what we're essentially going to be doing. So we're going to figure out the empirical formula, and then we'll figure out how many times that empirical formula goes into the molecular formula based on its mass. Right? We can use its mass to do so. All right. So for example here, hey, find the molecular formula for a compound if, with a mass of 82. The empirical formula is C3H5. Right? So C3H5, that's got a mass of 36 plus 5 is 41 grams per mole. Okay, so we know 82 divided by 41 equals 2. So we're going to take C3H5, right, and multiply that by 2. So its molecular formula is C6H10. So you see how we're basing that on mass? Does everybody see how we're figuring out how many empirical formulas there are in the molecular formula? Okay. All right, so let's do kind of them all together in one problem here on the next page. Same steps with one extra step at the end. Okay, for this one here, we've got, sorry, I'm going kind of quick. I'm just trying to make sure let's get this last problem in for the time. Okay, so we've got 82.8 grams of carbon. So I'm doing percent of mass right now. We got 17.2 grams of hydrogen, percent of mass. Now we're going to do mass to mole. 1 mole of C, 12.01 grams. 1 mole of H, 1.01 grams. We got 6.89 and 17.2 divided by 1.01. We got 17.03. So divide that by small. So we divide through by small. So 6.89. Get a ratio here. So we got 1 and divided by 6.89. We get 2.47. What is that pretty close to? 2.5. 2.5. So 2.47 is approximately 2.5, and that's what we're going to work with, right? Because the next step, the last step there is the multiply till whole step, right? It's the multiply till whole step. So we want to be able to multiply these numbers by something to get a whole number, right? So what do we multiply 2.5 by to get a whole number? 2. Whatever we do to one, we do to them all. Just like we divided through by small, we got to multiply them both by 2. So we multiply by 2, multiply by 2. So we get C2H5 as our empirical formula. That's our empirical formula. Okay? And then they're telling us the molecular formula is 58 grams. Okay, so the empirical formula's molar mass is equal to 12.01 times 2 plus 5.05. It's 29.07 grams per mole. So the molecular formula has a 58 grams per mole, right? We divide that by 29.07, right? You get 2. So we've got to go 2 times C2H5 to get C4H10 as our molecular formula. So we took the mass of our molecular formula, divided by the empirical formula mass to figure out how many of them were in there. Okay. Okay. There's only one other kind of wrinkle that we'll work on just on a separate day. That would be Friday, when we'll do empirical molecular formula stuff of combustion reactions specifically. Okay, those are kind of neat, but they work all the same way. It's a little bit of work up front to get the percentages of each component of each element ahead of time. But tomorrow, we're going to do our quiz tomorrow. All right. We can go over, well, we got 3 minutes. If you got a question or something on the homework, post question. I was on this morning during a couple of our meetings. I was like putting up responses to Google Plus questions on the community. Okay, or responding to some questions up there. So it's good if you're having issues with the homework, post in the community. Work the green worksheet. We can go over any questions you got tomorrow before the quiz. We'll have time, and then we'll take the quiz. After you finish the quiz, you can do test questions. Yo, what's up?
I don't know if I did this one right.
No, I wasn't really worried about having it now, but I'm going to start doing practice work and whatever, but make sure I'll get fine. That was up. We got so this one you got 2 grams of chlorine, 3 grams of chlorine. How much of this product are you making? So you can do it 2 ways. Either you take them both, solve for the amount of product, and see which one produces less. That's the limiting reactor.
How do we solve for the amount of product we have to
3 grams of
I got 3 grams per 9 of my home. I limiting reactions there.
They're giving you both reactants, so you got to figure out which one is limiting, and then go from there.
I was just confused where you plugged in
You got to start with those numbers, do split, and figure out how much titanium is made. Whichever one produces the least amount, then you're done. That's it.
Okay.
All right. So you got to do two problems. One starting with that number going to titanium, and the other one starting with that number going to titanium.
Whichever one can.
Right. Whichever one produces the least amount is limiting.
And then my answer would be how much titanium would be produced by the one right?
Because that's all you can produce with that number.
Alright.
Yeah. So it's just a limiting reactant, how much oxygen remains. I don't care how much product's made. I just want to know which one limits. So you guys, and which one we have extra, and how much of the one we have extra.
Convert like both of them to each like element, or like to.
The way I would do that is I would go 2 grams of ammonia, solid 4 grams of oxygen needed.
Okay.
And then that will tell me like, hey, if I need 3 grams of O2, that means I have 4.
Yeah.
So I got 1 extra left over.
Okay.
And then I know ammonia is also my limiting reactant.
Okay.
But if it goes like, oh, I got 5 grams of oxygen, then I know oxygen's my limiting reactant, and ammonia would be my excess. So then I would have to take my limiting reactant, 4 grams of O2, solve for the amount of ammonia needed
Okay.
to figure out, okay, well, how much of that 2 grams do I really need?
Oh yeah. Okay.
You know what I mean?
Yeah, I get that. Thank
Okay,
you.
so you might have to do an extra step
Okay.
depending on if you're lucky or not, right?
Okay,
Oops,
thank
sorry. Now I gotta go to class. My other class. Dang it.